coffee hour. Francois is from Belgium. He was educated initially as an engineer at the Université Libre de Bruxelles. He obtained his licence and doctor at the Université Libre de Bruxelles. He spent some years at Cornell and then returned to Belgium at the Free University of Brussels. Among his other, and that's his current affiliation, but he also is permanent Sacco professor and senior professor at Tel Aviv University. Francois is renowned for many things, in particular his work on broken symmetry. He received the 1977 High Energy and Particle Physics Prize from the European Physical Society and the 2004 Wolf Prize, both with Brout and Higgs. It's a great pleasure to introduce Francois Englert, who will speak to us today on gravity, geometry, and group theory.
Well, thank you very much, and I must say, before anything, that I'm very happy to be here. I've been often at Tel Aviv University, and I love being here. It's a university, of course, it's a top-class university, one of the best, and it has succeeded in keeping such a friendly and nice atmosphere that it's always a pleasure to be here. And this time even more so, because I come for the celebration of Yuval's birthday, and that reminds me that many times when I came as a Sackler Fellow, and I always was received with great warmness by Yuval, and I will not forget his secretary, Matilda, who always was extremely helpful and wonderful to me. So what I'm going to talk today is what I think to be a deep relation between gravity and group theory. Now, if I've chosen to say about that subject, it's not only because it interests me, but also because I think it is as an expression of my gratitude to Yuval, because I know these subjects were subjects which he made deep, a lot of important discoveries. Well, group theory is, of course, well known, and also in general relativity, and I thought it was appropriate to talk about this thing here. Unfortunately, it's not always easy to talk about all these things to a general audience, so this is going to be, of course, a colloquium, so I'm going to try to find the right balance, which probably I won't, but I will try. So, first, this thing has to work. That was a mistake. Okay. Okay. Yep. Yes, just for this, huh? Yeah. Okay. So what I want to do is just sketch very rapidly the history of gravity from its Newtonian beginning to how Einstein did it in a geometrical way. And then I want to discuss a possible, group structure which underlies gravity, which is a more personal addition to this. So what I will do, I will first very rapidly call how the crucial point between the Einstein and the Newtonian way, and I will illustrate this history through essentially also the history of the black hole and how it fits into all these schemes. Because the black hole, I think, is a nice way to illustrate all these problems. So let me first just start with recalling very simply this passage from Newton to Einstein. Well, as you all know, of course, when you are on a rotating disk, you seem to feel the centrifugal force. So this is the pseudo force that we feel, and which has to do with essentially change of coordinate of change of frame. Now, where do we see that more simply? That this is always proportional to the mass. Proportional to the mass, it means that because F equals ma, things that we all remember, then m drops out of the equation, and there's no reason that this has anything to do with anything else than the departure from the frame in which this Newtonian theory has been set. So this is the signal of a change of coordinate, essentially. It is this thing, and we are not in an inertial frame when you see the centrifugal force, the pseudo force. Now, of course, the remarkable point is that when you have bodies of different masses that fall into the ground, they fall, we know, at the same acceleration, and therefore, again, it's proportional to the mass. So that was, of course, the great idea of Einstein, that therefore this also should be somehow a pseudo-force. But of course, if you do that at one side of the earth or another point of the earth, they just don't fall in a parallel way. So somehow this could not be everywhere local in space. Well, it should not be local in time too, because you can, of course, as in the non-initial frame, change your frame and then you eliminate the thing. But there's a limit to the way you can limit. You can eliminate that if you are in a free-falling or in a free-falling lift or thing like this. When the thing hits the ground, the story ended. So this is only, of course, local in space and time. So this is the background of the geometrical interpretation, which tells you that everywhere you can locally find a frame where you eliminate gravity, because gravity is proportional to the mass, and then this is essentially why you can interpret the forces of gravity as something which is essentially of a geometrical character, and what determines the geometry is essentially the mass. The picture here, of course, is not a very good picture, but it tells you that if you have a mass which deforms the geometry, you see how you have a tendency to get into it, right? But you should not take that too seriously, because essentially it is a this seems to be something in space, but it's only not space which is curved, it's space-time which is curved. I mean, time is curved, what does that mean? Well, the simple way, again, let's go to the black hole, we'll see what that means, that time is curved. Well, we can go back to all the history for that, but first let's see how the idea of the black hole was put into Newton's framework by two people. The French say always that it's Laplace, which is of course not right. And so it was Michel who first realized that, well, not necessarily in a very correct way, as we shall see, that if you have a big star of radius r, or can be smaller than that, but if it's on a radius r, then writing the conservation of energy, the kinetic energy and the potential energy, you can say, well, if the thing can go at infinity and reach infinity just marginally with zero velocity, then you have a relation on r, and if the mass is bigger than that, they won't reach infinity. So therefore, if you would have just, well, let's assume that light is something like a little particle. At that time, you could say that already. But of course, not quite with that equation, but it doesn't matter. If you do that, you say, okay, so if R is such that it's smaller than that ratio, then the light will not arrive to infinity, you won't see it. That was the reasoning of Mitchell and Laplace. And so the thing becomes dark. And so that was the Mitchell-Laplace black hole. But Laplace realized that something was wrong with this. And in fact, he took it out. He said it's not right. Because, he says, it's not true that you can't see it, because if I send the light into it, it will reflect on this. And it will reflect, therefore I will see it. So in his second paper, he took it out. And this was very clever, in fact, because there's no much way in Newtonian mechanics to allow this. But we can take it out. We can take out this defect once we understand what general relativity is and the curvature of time. Who is the one who first understood that? Well, we have to go back further in history. Let's go to Zeno. Now, Zeno, as you all know, says that, well, you see, if you throw an arrow to this guy, it will never reach him, because it has to go to the middle, and then to the middle, and then to the middle, so it has to go to an infinite number of steps, so the guy is safe. Apparently, this guy thinks that is true. And so, well, this is just what we know in our modern way. Would say, well, you sum the geometric series is this, and you get just twice the initial step by summing this infinite number of steps. So, well, what Zeno had in mind was essentially to contest some idea of the infinite structure of space, or if you wish, what we would call the continuum. Well, today people say, well, this is a stupidity, because, of course, if we do the same thing with the time, and say, let's say the time is proportional roughly to the position, then you do the same slicing in time, and of course then you have a new geometrical theory, and then finally delta t is equal just to 2 times the first step. So all what Zeno has done is to say that before twice the first step, then you will not reach it, which is of course true. But that doesn't tell you that is not. So this guy should not be as happy as he looks there, because this is not true. But, there's a but. Suppose I have another law of the way the arrow goes. Suppose I take a logarithmic law. And if I take a logarithmic law, then I have that relation for the nth step. You see immediately. And then what happens is when you compare 2 different steps in time, then you just find that every step takes the same time. So you don't have a geometric series, you have an arithmetic series, and just every time you do the same number of times, so you will never reach him. So the guy is very happy again. So finally it depends how time is related to space. Now, what has this to do with a black hole? Well, it has to do. When you do Einstein theory, you measure the distance in space, the distance in time, and express that the velocity of light is constant, which can be expressed at the constancy of this quantity ds squared, which is t squared plus r squared plus the r squared of space. Well, the Einstein equation, which is geometry in space and time, modifies this coefficient by what one calls the metric coefficients, and the g, so it's a quantity you call g with 2 indices. If it's 1, 1, it means time. If it's r, it means grr. If it's grt, it means r and t, namely dr dt, in the value of something which is invariant for every observer. So the ds squared, that corresponds to a point-like particle of capital mass m, or just a star of mass m, outside some region r, which is equal to 2gr, as Laplace and things mission computed. Well, by the way, the fact that they got the right number is a consequence of two things. One is just dimensional analysis, and the second is that, well, we called it Buckingham Theorem in Boston. Buckingham Theorem is once you make dimensional analysis, generally you're not got wrong when you get something, you multiply it by a factor of order 1 to know what it is. And it turns out that the factor came out to be 2. That, I think, is an accident. But the fact is this type of thing is true for when there is an accident. And now, what happens? You see, the energy, so this is the way it's modified. I'm not going to, of course, discuss this in detail, but a consequence of this is when you apply Einstein's equation, you compute the radial motion, and you just find for a radial motion that energy is conserved with a slight difference, which is important. The time which I label tau, is just the time of someone which goes with the particle itself if you have a test particle. And that time is essentially the ds which is there. The d tau squared is minus ds squared, if you wish. So you have this law, and let's suppose you are close to some region where this, it's not the edge of the star. We'll see in a second what it is. The region where obviously you can't use this metric, where r is equal to 2gm. What was the limit Laplace said to the star mass? Here it's not the star. But so we have, if this is constant, then what happens? Let's see what happens first to Zeno. Is he right or is he wrong? Well, he's right and wrong. And the point is this: let's suppose we are close to a distance, coordinate distance r, which is close to r equal to 2m, and let's call x the coordinate where you go towards what will turn out to be the black hole. And we are at the coordinate distance L from this, let's call it the horizon, because that is what it is. And it's here. And then you see that because 2gm equal to r at that point, which I marked there, then dx over d tau is of order of 1, which it means that is just that this, in the proper time, is just proportional to tau, and Zeno is wrong. We have seen that if time and space are proportional, then you just go through, and the guy should not be happy, and he's going to be killed, as you should expect. In fact, it's more complicated than that, because he will have some problem to stay there. But let's see what happens with someone who is looking at the guy. Well, if someone looks at the guy, he will do that in the same time as the dt, which is there, the time that the external observer, let's say, uses. Now, if he now do that, he will solve that equation which is there for dt, the ds squared we know in the vicinity of 2gr r equal to m is of order 1, so it's negligible compared to the other term, so you just put it equal to 0, good approximation, and dx dt is given by 1 minus 2gm over r, which in using this r is equal to L minus x, so you get this, so you just integrate that equation, and this is just exactly what happens for Zeno to be right, because we have the same law as we had previously, right? Just the same law, which is here, we get it here, and so Zeno is right, you will never reach this point. Well, I mean, for the external observer, you don't reach. He doesn't live long enough, whatever how long he lives, he doesn't live long enough to see the thing coming to the black hole. Well, with a little bit of stretch of imagination, you can see what that means. In a sense, you have to do it a little bit more carefully, but essentially what happens on the other side, because if you never can already send nothing, and there you can send things, but you will not know that it arrives there. So essentially you will not know anything about what is going to be there. So you lose information, and that is why, that's what corrects the problem that Laplace had, that the thing cannot be really dark. It could be dark because, at least classically, because of this effect, that you lose information about what cutting hair, and that won't be any reflection, in fact. So there is a horizon. If you have a mass somewhere here within this region r equal to gm, if you have a mass there, there is a region in which you lose all information. Now, Bekenstein, from different point of view, related one, which I don't want to discuss here, arrived the idea, if you have something in which you lose some knowledge of it, generally you have entropy. And Hawking said that if you have entropy, you should have temperature. In fact, you have a collapse. That's a time-dependent process. If a star collapses, and then it should emit particle quantum mechanically, you can compute that. That's a very easy computation quantum mechanically, and you find that the particle created seems to have a thermal spectrum, essentially, and they have a temperature which is inversely proportional to the mass, which I wrote there. Now, by the way, now that I am in relativity, c is 1. I don't write the velocity of light. And once this is done, then the Bekenstein idea that the horizon contains entropy becomes completely precise. Even the coefficients are fixed, because if you see the first equation, which is there, which is just an identity, if you read it carefully, it reads delta m equal delta m. But the first term is just this temperature. So you can also read that as dE is equal to TdS. Therefore, you can compute the entropy, and the entropy is equal to this, plus an integration constant in principle when r goes to 0, and you get the famous relation of the entropy of a black hole, that the entropy is proportional to the area of 4 pi Hg. And possibly an integration constant. Now, this is extremely important because this is a macroscopic space. It's extremely important from the point of view, the conceptual point of view, of what we should do in order to quantize gravity, essentially, because you see, you have a macroscopic object here, and this macroscopic object has an entropy which normally quantum mechanically should be counted as a number of states. And therefore, this macroscopic object essentially catalyzes quantum effect up to the macroscopic scale. So it's a very important thing, and not only has the Einstein interpretation of gravity solved the dilemma, or let's say the inconsistency of the black hole of Laplace, but it has left us with a new problem, which in a sense contains a lot of inconsistencies, potentially, which is the fact that the black hole has entropy. There is a region we don't understand, and all this is related to the paradox of information, and I'm not going to go into that, but please keep in mind that the black hole is something very important, because now I switch to my third point, which is the conjecture, group structure of gravity. This is more personal. Of course, there's a lot of literature. Well, not that a lot, but there is. And I'm not going to give all the references here, but you can find it in the 2 papers which are there, kind of complete reference with respect to that. So, because now I'm going to try to make a contact between general relativity and group theory, and I'm not totally sure that everybody here is familiar with all the subtleties of group theory, and we have to generalize group theory here, by the way, at least conventionally Lie group. So I'm obliged to give a lecture on group theory as an introduction. So to get a full lecture on group theory, I hope I will be able to do it in 10 minutes. It means that I am going necessarily to be sometimes a little bit sketchy. But let's try. So I'm going to talk about Lie groups. Lie groups, like the rotation group, is a group acting on a continuum, and it's given by generator. SU3, for instance, is a Lie group. There are generators which commute between themselves, hypercharge, isospin. For rotation, the angular momentum along an axis is a generator. So quite generally, a Lie group can be done in what's called the Cartan representation, or the Cartan presentation, where you write the generator of the groups. There are all two classes. You first take all the maximal set of commuting observables, if you wish, the number of the generator that commutes, call them HI and HJ, T3 and Y, for instance. And then step operators, G plus G minus in the angular momentum case, and call them E plus alpha and E minus alpha, and are proportional, as in the case you know, all of them by some quantity which are called root, which can be seen as vector in the space of the commuting generator, whose number is, let's say, R, and this is called the rank of the group for these simple groups, which don't go in detail. And we can close the commutation of E alpha and E minus alpha, like G plus and G minus, by going back to the Cartan generators, which is given by that relation. Now, the trick is the following. You can always find some simple roots that are roots such that all the roots are always a sum of positive ones, involve only positive, eventually zero, positive coefficients, and negative roots, which can negative coefficient. You can check for SU3, which everybody knows, in which you have, these are the simple roots. And you can check that all the roots, which are just a coefficient of E alpha, can be written as a linear combination of simple roots with integer coefficient, which are never negative or never positive. There are two sets. So everything is the Cartan presentation. You have everywhere the Cartan generator, and you have the positive and negative step operator. And one other concept, it kind of starts like a bridge lesson, right? It's simple, but at the end you have too many things, and so probably after a while I'm afraid I'm going to lose the audience, but let me try not to. So, and there's a subgroup that will play an important role. It's the subgroup of the Cartan subgroup, which is the commuting observables and the positive roots. That's called the Borel subgroup of the group G. Now, this presentation is what people generally use, but to see conceptually how the group functions, it's better to go to another presentation, which is the Chevalet-Serre presentation. It's essentially the same thing, but you focus on the simple roots. You focus on the simple roots, and this is just, you rewrite the simple roots as linear combination, call them A alpha. You call the simple roots, simple step operators, call them E beta, and if they are negative, call them F beta. That's simple. And the closure relation just reads that E alpha F beta is H alpha with a coefficient of 1 or 0. That's the interesting thing. And because you have redefined this that way, then instead of H having H EB is equal to alpha EB, you now have a matrix which is E alpha beta, which is called the Cartan matrix. Now the Cartan matrix, which is here, I have written here for one of the groups which exist. All the groups have been classified by Cartan, the Lie groups, and we have them here. And all these groups can be written in terms of the Cartan. Now, once you have the Cartan, you can write all these relations. And now what you do in order to find the other generator, well, you just take commutators of the one you have. But there is now a very nice thing, which is the Serre relation tells you if you take one generator and then take multi-commutator, that arrow here stops very fast. It stops when this quantity here is equal to 0, where this is the matrix. For instance, if you would have a Cartan matrix where you have -1, this stops at the level of 2. So if you take the 2 commutator, E beta, E alpha is 0. So what the idea of this representation is that, in fact, once you give yourself the Cartan matrix, you know everything. Because you can write a commutation relation for the simple roots, and then the Serre relation tells you what are the other roots, and that's it. It's finished. So every group is done. The last step I want to say is that there is a nice way to represent the Cartan matrix by what's called a Dinking diagram. Each of these bubbles represent a root, and the line here represents the non-diagonal elements of the Cartan matrix. The diagonal element by definition here are always 2, and that can be easily verified. And the fact that when you put a line here, it means that the upper line, which is here, is -1. You can have a Dinking diagram with more than one line, then you have -2, -3, and to get, here it's symmetrical. If not, you have to put an arrow to know if you are above or below the line. In other words, I don't go in detail, but this matrix is entirely encoded here. So you write a set of bubbles, and you write lines between them, and in the Cartan matrix, you use the same thing, you have all the groups. Now, do you have all the groups? Well, you get much more. Because something happens sometimes. If you start putting anything you like here, by the way, it has to be negative integers for this to work, what will happen is that this quantity here, the Serre relation, will not stop. So instead of having a Lie group, you're going to get an infinite set of generators. And that is essentially what is called a Cas-Moody extension of a Lie group. You do exactly the same thing as a Lie group, but you do it that way. And you write a Dinking diagram. You deduce what the Cartan matrix is. You write all the commutation relation. And then if the Serre relation doesn't close, well, you have an infinite number of generators. And that's what happened. For instance, as a given example, simple one, which will be thing, and this should be the end of my lecture of group theory, this transparency. When you have, let's say, the group which I called E8, by the way, there are, Cartan and found, there are 4 classes of groups which are, which exist in any number of dimension, like the rotation groups in any number of rotation and things like this. You have 4, and you have exceptional groups, which do not belong to this classification. There are 5 of them, and the largest one is E8. So I just wrote E8. This is the Cartan matrix, and this is the way you encode the Cartan matrix in a nice graphic, which is this Dinking diagram. And I label for future reason these by 5, 6, 7, 8, 9, 10, 11. We'll see why in a moment. Well, I could play a game. And for instance, I can just add here 3 bubbles and call it 1, 2, 3. That's why I call this one 4. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, right? Now, is this a group? Well, you do the same game. From this you write the matrix. You see it's the minor modification. You have just 3 lines and 3 rows more, which are exactly the same as here. So it looks that you haven't done very much. But if now you look the Serre relation, they don't close. In other words, now you generate an infinite set of generators, and this is a Kac-Moody algebra. There's 3 things more than E8, so you call it E8+++, or you call it E11, because now you can read from 1 to 11 here instead of 4 to 11. So this is E11. As an example, this is the Cartan matrix. You do all the game, and you find all the generators if you have an infinite time at your disposal. And so now the number of group generators is now really an infinite vector space. The rank of the group is not that big, it's 11, number of commuting generators. So, finished with my lesson of group theory. I hope you have assimilated everything, you know everything about it, right? Fine. So now we'll apply it. We'll apply it. To what? Okay. We'll apply it to gravity. Well, first what I've done with E8, I took E8 as an example, but I could take any kind of group. In fact, then you can play the same thing and don't go in detail, and you can write Kac-Moody generation, which extend the group and so on. But I want to extend it in a quotation mark physical way, right? Let's take a theory of gravity coupled to matter. But let's take it, after all, this is a common game nowadays within theoreticians, which one day they think they will make some contact with experiment. Take more than 4 dimensions. Take a theory with more than 4 dimensions and saying that apparently we seem to live in 4 space-time dimensions. So after all, well, that's not necessarily contradictory. Let's suppose the other dimensions are very small. And the simplest way to have them very small is just to say that there are lines as usual, but to finite extent. In other words, they are circles. So this is called the toroidal compactification. If they're very small, well, you don't see them. Well, you don't see them, but of course there are many dimensions, so there are many components to this thing I call the metric tensor, which is the thing which multiplies this invariant quantity ds squared, which is the black hole, this g, tt, and the grr, which I talked about. More generally, you have these things. And so if you have now a big theory, and so you have relativity coupled to matter in a large number of dimensions, you can reduce, if d is the number of space-time dimensions, you can see what it gives in a slower number of dimensions, let's say 4, or let's say even 3 space-time dimensions. Why 3, we'll see in a second. Now, if you take 3 dimensions, and you make this compactification, as I say, in very small distances. Well, if it's very small distances, you're not going to excite any energy in this thing. It would cost too much energy. You can put it to very small. And then the theory is insensitive to the shape of these torus, or these lines. Their relative orientation, all of this will drop out. This will be a symmetry of the theory. In other words, any deformation of the internal dimension will not be felt, or at least will be a symmetry of the theory in the lower dimension. Now that symmetry is just a linear group in d minus 3 dimension, if I compactify to 3 dimension, because I just deform the thing. Now, if you do now some fine-tuning of matter, you don't put any type of matter. You choose your matter in such a way, and this, by adding something which you have chosen intelligently or stupidly. And, but you tune in very nicely the d, the scalars, the fields, and so on. Well, it turns out that in some cases, instead of g minus 3, you get another g, instead of the linear group, you get a group with the same rank, but which is much larger. This is because there are other fields and they combine nicely. Now, lo and behold, there is one example of this when the tuning corresponds to what people call the 11-dimension supergravity, which from time to time you hear, especially by people who like string theory, and they say even that one-day string theory, which as everybody knows is a theory that doesn't exist, will come into existence by going to a generalized called M theory and think, and 11-dimension supergravity is the lower energy bound of this. Now, people have heard these words. It looks a little bit like slogans. In fact, I think they are. But nevertheless, it's an interesting thing. So if you take 11-dimension supergravity, which it just corresponds to one of these fine-tunings, and for this fine-tuning of 11-dimension supergravity, instead of GLD minus 3, you get E8, the one I've done before, the one I showed before. But not only you get E8, you know these are roots, that is some generators, these are simple roots, corresponds to some generators. These generators have parameters in this group, and the parameters can be identified with these metric components which measure the orientation of the different lines in the non-compact dimension, and which are function of the 3-dimension which are there. These red ones correspond to these fields, essentially, which measures the length of the torus and their relative orientation, and this is the extra field which enter in 11-dimension supergravity, which is called the treeform, which is a generalization of the Maxwell, let's say, the Maxwell field in this context. And these fields don't parameterize the whole group, they parameterize a subgroup, which I call the Borel subgroup, and this is how it happens. When you do the computation, this is what you find. Clearly, I'm not going to do that. Now here is the idea. Now, you see what this happened, and this begins with 4. So why not go to 0? In other words, why don't we compactify fully the theory? Well, the problem, of course, the more you compactify gravity, the less you have dependence on variables. And also you have another problem, namely below 3 dimensions, 3 gravity apparently doesn't exist. Who cares? Because we now have a way to see that there is something hidden in gravity which we wouldn't have expected, which is this group. So now let's define what we call the compactification to 0 dimension by gravity by just adding these 3 nodes here. And then we have E11. That's just what in my brief introduction to group theory, I call this infinite Kac-Moody algebra. So now the question is this. Can we use this? Because now we have, in a sense, you have an infinite symmetry acting on nothing, right? Because once you have reduced to 0 dimension, things depend on nothing. But they still have a tensor structure, that they still have indices that you can copy from what they are here, and I show them here. And so the idea is maybe, that's an attempt, try to do this, try to find an intelligent way to reconstruct the theory which has that 11-dimensional symmetry, and maybe there you're going to find, for this case, for instance, what you really mean by 11-dimensional supergravity, or maybe something else, or maybe more, or maybe less. That's the attempt. Now, you can construct a thing that I will not explain how here, but you can construct a theory which is invariant under E11. And I will not discuss how, but I will show that it has some interesting property, and come back to black hole in a second. So, well, first let's briefly see what happens with these fields. These are just the metric, the gravitational field of Einstein, which we now go to the full set of 1 to 11 for the diagonal, and here we have one component of the 3-index form, which is kind of a generalized Maxwell field, as I said. But where are the other ones? Well, you decompose what's called the adjoint representation of E11, that means a set of all generators, into tensors, which is in fact irreducible representation, the linear group L11. And you find that you can represent this in terms of these tensors, label them by the level, which means the number of time in the decomposition this root enters. For instance, at level 0, you just find these, when this doesn't enter. And this is essentially the structure of gravity at one point, strictly speaking, because it doesn't depend on any dimension. But you can invent a way to do this, that it may have something to do with dimension. That I don't come in. At level 1, you find this business, which is a three-form potential, which is a generalization of the one potential. At level 2, you just find essentially what would be the magnetic dual of this. And at level 3, you find essentially the dual of gravity, essentially, which is a very complicated object, which you find here. And once you're above level 3, and some of them, in fact, in level 3, then you find something you don't know what it is. So that now you have to be clever or abandon the problem. For the moment, I'm not going to try to be either one or the other. I'm just going to skip the difficulty. But there are an infinite number of fields. You have to find what they mean. So now I want to see that there are indications that this symmetry plays an important role in Einstein in the theory of gravity. And for the moment, I stick to this example of supergravity. There are in theory of Einstein with these forms, which are like Maxwell's equation, I say, there are solutions corresponding to what is called brane. Brane is just a generalization of a point in many dimensions which emits some fields. And for instance, in the supergravity, there are two brane type of solution, the 2 branes and the 5 branes. Now, these branes can be extremal. What that means? That means that if you take 2 branes of the same charge, like 2 charges, you can find a situation in which the repulsion, the electromagnetic repulsion, compensate the attraction of gravity, and then you can pile up a lot of them, and you can find solution. If I'm in Einstein theory, you can find a solution of these 2 and the 5 branes, and I've written them down here. Now, I've written them down not for you to read what it is. I don't want overly to terrorize anyone here, but just to say that, to see that there are a lot of algebraic type of quantity here, and only one function which depends on space-time. And in fact, in Einstein theory, that function is essentially what's called a harmonic function. It's a very simple function in any number of dimensions in which these branes are not. These branes are supposed to live in the compact dimension, but they give their field, of course, in the non-compact one, where we are supposed to live. And so, in the 11th theory, we don't know what we are because we are at 0 dimension, but I can show that you can reconstruct at least partially space-time, at least 1 dimension. That can be done neatly. More than 1 dimension is conjectural for the moment, but 1 dimension you can do. And in 1 dimension, what do you find? You find that from the 11th theory by itself, without having a look at Einstein's equation, the algebraic structure of the equation can be found from the 11-dimensional theory. And instead of that equation, you find that equation in 1 dimension, but there are sufficient fields to guess that maybe you can reconstruct space-time further and have the solution in more dimensions. And in any case, the algebraic structure of these extremal brane is totally encoded in this group E11, this Katz-Moody group. Can we go further? Yes, because the 2 brane and the 5 brane, they can intersect as many times. And when they intersect, and the non-diagonal curvature tensor, very complicated object in Einstein theory, can be solved, and to tell you when they can intersect and when they can't, to be a solution of Einstein's equation, coupled to 4. And if you do that, then you find that there is an equation, which I wrote here, and there are some things here. This is when there are coupling to scalar fields. It's a general equation. There are no coupling to scalar fields in the examples I give, so you forget this. D in our case is 11, because I took as an example 11-dimensional supergravity, and these things are 0, and we find that this is what you would call a Diophantine equation, because this is the Q and QB are the number of dimensions of two of the branes which are supposed to intersect to give a solution of Einstein's equation, and Q bar is the dimension of the intersection, which has to be an integer. So you look for integer solutions of this. This equation is nothing else, as I say, as the Einstein solution for the non-diagonal component of the curvature tensor. And when you do this, you find that the two branes can intersect in 0 dimension. That means that they can be in orthogonal dimension. That's still a solution, but not with no dimension in common. The 5 branes can intersect in 3 dimension, and the 2 and the 5 brane can intersect in 1 dimension. Does it have a meaning that in group theory? The answer is yes. These branes are generated by some fields coming from the tree form on the dual or things like this, and the metric, it's complicated stuff, but they are generated by some fields. Some fields are related to generator. Yes, they are related to generators, and the generators, the generators are parameterized by these fields, right? So the generators are characterized by roots, things. So we can find what are the generators which are involved in intersecting branes and compute the roots in E11, and we find, lo and behold, that in order for that complicated equation to be satisfied, it simply means that the roots have to be orthogonal in E11. Now, let's see if we can. Now, these fields have also to be one is the time, have to be the time in common. And if you now look the maximal number of orthogonal roots that you can make with the time in common, you find that there are 4 of them. And if you now write these 4 intersecting branes, you see here this is a 5 brane. It has 3 index in common in addition with the time. The 2 branes have no index in common. The 2 branes and 5 brane have always 1 index in common, 9, 9, or here 8, 8. And this is the maximum number you can make of orthogonal thing with 1 dimension, with these, with having the time. And then these build a set of intersecting branes, and you can see what is the field they radiate or in the non-compact space. And lo and behold, this is a black hole. And so you get the black hole as a solution of this equation in the group theory, acted in the case of E11. You can play around, because if there is one solution and E11 is a symmetry, you can find another solution. The other solution, for instance, can be obtained by some discrete subgroups called the Weil reflection in this group. When you do that, you generate other branes which are here, and these branes are labeled by something else, which are Kaluza-Klein monopores or things like this. Is the type of thing you get. Doesn't matter. You have another solution, which in 3 dimensions gives exactly, in 4 dimensions gives exactly the same black hole. Now, in fact, it's interesting because from the last form, there's a connection to what people call string theory. And in string theory, this is my nicest transparency, so I want to put it, right? In string theory, this is the black hole. What you do is you take the expression of 11-dimensional supergravity, which is here, and 1 dimension you take out, and then you get 10-dimensional string theory. That's the hocus pocus that you do in string theory. And the interesting thing is that in string theory, using a few arguments, which are what they are, you can compute the entropy of this black hole, and you do find the correct entropy with an integration constant, which is supposed to be 0. Now, this entropy is not our original Schwarzschild entropy, but you can show that it's related to an isotropic, isentropic transformation, which I may discuss later or privately. So here is represented what this solution means. We have 6 compact dimensions and 4 non-compact dimensions. So this general gray area is the 6th brane which fills up completely the compact dimension, in which there are a set of 5 branes, which are here. These are these semi-transparent branes. And then there are 2 branes which also exist and intersect the 5 branes. One dimension, in fact, can stop on them. And then you finally have the equivalence of the 4 branes, which after a while reflection are this, and going to the string, it's a momentum. And so you have momentum running in this intersection. And computing now the full set of this momentum, this is how you compute essentially the number of degrees of freedom quantum mechanically you would have, and that's how you compute this quantity by a counting of state in quantum mechanics. Now that, I think, is important, although, of course, there's a lot of things which are unclear, in particular the relation with the Schwarzschild black hole, and I hope I will be able to find something on this, but not sure. And so let's come to my last transparency. What I've tried to do is to sketch the little bit main step of the history of gravity up to today, in a sense, with putting some insight that I may have, or I don't have, I don't know, some conjecture, let's say, about the possible existence of a group theoretical structure which underlies the gravity as we know it. And by the way, it's not only in 11-dimensional supergravity, there are many others, but this is not what I want to say. And essentially, that it could be that there is a Kac-Moody algebraic structure underlying gravity, and then we have to reconstruct space-time. We have no space-time. So is this possible that this algebraic structure is the underpinning of gravity and space-time and solves everything? Well, I doubt it, but we never know. So let's try. Thank you.
Thank you very much.